Okay, so I sent you out this worksheet to do last couple days ago, and I originally asked you to do it and hand it in, but let's not do that. I'm just gonna get uh, go over this now, review it like I would in class, and so that you can sort of hear and see the intricacies of kind of details, and to distill what you need to do out of it. I know it's confusing. There's a lot of information here, and that's why I want to do this. And hopefully it'll be clearer now. So I gave you a list of molecules, their chemical formula, and again for these is that you have to be given the chemical formula first, and then from that you can figure out other information. So we're going to find the bonding structure, the shape of the molecules, polarity of each bond, now the molecules polar and nonpolar, formal charge of the hybrid on the central atom. If the bond is should be sigma, not S, or P, which I mean pi, sigma or pi. And what is the best possible structure for a few of them? Okay, so the last video that we covered a lot of information about hybrids and shapes and all kinds of things, and I'm basically just distilling it down to what we given a structure. What are the things that we're going to be looking for? And kind of just get the answers. And then ideally what you would like to do is be able to understand why you had your answers based on what I talked about in the last PowerPoint. But let's get going on it. And so what you would need to do these, you need a couple things. You need a periodic table. You would need electronegativity table that that was on the last video, and you also need that chart with the shapes and the hybrid orbitals. Okay, so for the test you're allowed to have those, and I'll be more specific about what you need, what you're allowed to have on a test, and so forth. Now let's just get done with this. You guys have been real good about getting in your work. Hopefully that you picked up some, picked up on what's been going on here. You have the PowerPoints at your disposal for the rest of your life if you want. Okay, as long as there's YouTube. And if you move on to chemistry, if you continue with Edison, take 122. And hopefully we'll be back in the classroom. Maybe. There we go. So the first structure I gave was SO4. I said 3 minus, but I meant SO4 2 minus, sulfate. Okay. And I also said there's 4 structures. Actually, there's 5. And I'll be, for the test, I'll make sure that I get the details exactly right. So the first thing you do is you figure out the number of valence electrons. So sulfur has 6 and each oxygen has 6. You can find that out from the periodic table from what column it's in. Remember, column 1 has 1, column 2 has 2. All the guys in the middle will have 2, usually, unless told otherwise. And then starting in column 13 with under boron, there would be has 3. Column 4 has 14. Column 14 has 4. Column 15 has 5. Column 16 has 6. Column 17 has 7. And really, you're just dealing with the top right atoms like fluorine, chlorine, oxygen, nitrogen, sulfur, silicon, and so forth, and hydrogen. Okay, so here's the number of valence electrons. The skeletal structure, you put sulfur in the middle because it's lone atom, and also more particular, it's the least electronegative atom. Okay, and then put the oxygen around it. And then what you do, given that, the outside atom will get the number of lone pairs and bonds that atom will get. Okay, so in this, so it goes. So fluorine And anything under it will get 1 bond and 3 lone pairs if it's an outside atom. Oxygen and everything under it, if it's an outside atom, will get 2 bonds and 2 lone pairs. Nitrogen and other atoms on below it in the periodic table will get 3 bonds and 1 lone pair if it's an outside atom. And carbon and under it will get 4 bonds and no lone pair. Okay, some typical things about carbon you usually be found in as a center atom. The center atoms do not have to have 8 electrons around them, because they, especially the only ones that are limited are the second row, and we'll see that in a couple of these. If you're in row 3 and beyond, like we'll see in this example, you can have more than 8 electrons in the outer shell. Okay, so let's get started here. So we have this as our structure, sulfur and 4 oxygens. So you put 2 bonds and 2 lone pairs around each oxygen. Don't care about the sulfur right now. And then what you do is you count up all the dots. Okay, each dash is 2. So there are a total of 8 dashes. So that's 8 times 2 is 16. And then there's 16 dots. So you have 32 dots, just like the total number of valence electrons. So this possibly could be a structure. So we're going to use, there's nothing wrong with it. All the oxygens have no more than 8 bonds. Okay, that's the, 8 electrons around it. Okay, this guy has 2, 4, 6, 8. So, and sulfur can have more than 8 because it's in the 3rd row. So this is a possible structure, and we'll take a look at to see if it is the structure of sulfate. So I asked for 3 more, but there's actually 4 more. And what you do, from the last PowerPoint, I said whenever you have, and even during class, whenever you have a double bond on oxygen, one of those, that is one of the pi bond, can move out as a lone pair on the oxygen. Okay, so whenever you have a double bond on oxygen, okay, what you can do is you can move one of those lone pairs, and so now you can get this situation right here. Okay, so one of the oxygens could have that done. 2 out of the oxygens can have that done. 3 of the oxygens can have that done, and all 4 of them. And there are 5 structures. I'll call this A, B, C, D, and E. Okay, now this structure here, this is the only possible structure that it can have. Now this guy down here, B, can actually have more than one structure, the resonance structures, because this single bond can flip around, move around this sulfur. Okay, and so you can get a total of 4 different structures here. Okay, and they're all basically the same. What they do is they rebound back and forth on each other, and we call those resonance structures. Okay, and we'll show them in the next slide. Structure C, you can do the same thing. Okay, so it has 2 single bonds here, but those single bonds can move around, so you can have more than one of these. So this can have resonance structure as well. Okay, same thing with this guy. This double bond can rotate around. Okay, move around, and and you can have 4 more of these structures as well. And this is also a resonance structure. This one, the double bonds cannot move around because there are no double bonds, and so there's only one of these. Okay, so both A and E are not resonance structures, but B, C, and D, which we'll show on the next slide. So here's the possible resonance structures, and they get, it gets kind of hard to keep on drawing them, try to get them right. And so on the test, I might ask you to just write a couple of the resonance structures, not all of them, or maybe just tell me that they have resonance structure. Okay, so take a look at this. So this structure number B that we came up with, letter B, and you'll notice it has a single bond here. Now it's moved here. Now it's moved here, and now it's moved here. So these guys, this is basically one structure. It just resonates through. Okay. Structure B. Okay. here you see the two double bonds, and here now they're over here, and now they're up here, and now they're over here. Okay. Now I might have missed one. I'm not sure here, but they go back and forth, and so this has resonance structure as well. Okay. I think I'm missing one here. Okay. All right. And then and D can do the same thing. This double bond can move around, and so B, C, and D can have resonance structures, and you should be able to draw a couple of the resonance structures of these guys. Okay, so let's move on here. So the shape of this tetrahedral it just has 4 connections, no lone pairs on the center atom. And if you look at the table that I gave you, you'll see that. And also, if you look at the table, is if it has four attachments, no matter what, the hybrid is going to be sp3. So this is sp3 as well. The bond polarity. So what I'm asking you to do is figure out the polarity of each bond. This is actually simple because all of the bonds have the same bond polarity. And the way you figure that out is you take the electronegativity table. Again, you're allowed to have the periodic table, electronegativity table, and the chart with the structures and the hybrids on it. So let's just figure out how you do that. So we're just taking one of the bonds here. It doesn't matter which one. So you have a sulfur and an oxygen bond. I left the bond out here. Okay, sulfur has electronegativity at 2.1, and it's pulling the electrons this way, so I give it a minus charge and have an arrow, and this arrow should be length of 2.1. Okay, the oxygen has electronegativity 3.5. It's in the opposite direction, so plus, and these are arbitrary. I could have had made this one plus or minus, but but they're opposite directions, but they're not equal in their direction. So it's 3.5 this way and 2.1 this way. And then what you do is you add the two up. I don't know if you guys have had vectors, but what you're doing is basically acting a vector. A vector is has magnitude, which is the 3.5 and 2.1, and the direction of the arrow is direction. So you add the two together, and the resultant of that two is this is pulling towards the oxygen. I did bad math here. This should be a 1.4 plus 1.4. And it's important that you actually put the plus, because it tells you which directions go. Now, in the last PowerPoint, I told you that you could figure out the polarity of the whole molecule if you know all the bond polarities of all the bonds, and you can do that. But you probably need to get out and draw this out and do vector math, which we won't do here. And instead, what we're going to do is just come up with the polarity of the molecule through the tricks I gave you. And I gave you a couple of tricks, and the tricks that we're going to use here, since we're just looking at chemical, we have the bonding structure, is you look at the center atom, and if the center atom has the same things attached, then it's nonpolar, and if it has different things, it's polar. All right, so and be careful about what I mean by thing. So again, if you look at water's H has there's an oxygen in the middle, and oxygen is connected to hydrogen, so it looks like it's attached to the same thing. But if you look closely, it also has two lone pairs attached to it. So oxygen has more than one thing attached to it. It has lone pairs and hydrogen. So so you can tell by looking at that that it is a polar molecule. Okay, now when you take a glance at this molecule here, it looks like it's going to be nonpolar because all the sulfur just has oxygens attached to it. Okay, but the key thing here is that the molecule is charged. It's SO4 2 minus. That means the whole molecule has a charge of 2 extra electrons at it. And what that does is it makes not polar molecule has both plus and minus. A charged molecule just has a charge. So this molecule doesn't have a polar or non-polar. All right. Okay. So, okay, you have ask you to figure out formal charges, and the way you figure out formal charges, you take number of valence electrons minus number of bonds minus number of dots, and that'd be the formal charge. So there's for the oxygen, there's nothing but the double bond and single bond of oxygen, so I'm just going to do that. So for double bond oxygen, there's 6 minus 2 bonds minus 4 dots equals 8. Okay. The 4 comes from the 2 pairs. All right. If you have a single bond of oxygen with the 3 lone pairs on it, 6 is the number of valence electrons. It has one bond minus the 6 valence electrons, 3 times 2, and so is the formal charge minus 1. The sulfur on the one that's lettered 1A, I mean. Okay, sulfur has 6. This structure had 4 double bonds, so it has a total of 8 bonds. So it's 6 minus 8 minus 0 equals minus 2. So formal charge on the sulfur on A structure is minus 2. The sulfur on B structure has 1 less double bond, so it's going to be 6 minus 7, 3 double bonds and 1 single bond. And so it had minus 1. The sulfur on structure C had 2 double bonds and 2 single bonds. So 6 minus 6 and no lone pairs. So none of the sulfurs have lone pairs on them. Structure D had 6 valence electrons. It had 5 bonds, 1 double bond, and 3 single bonds. And structure E had all 4 single bonds, so the formal charge is plus. Now, this table over here gives all the formal charges of all the atoms. So structure A had nothing but double bonded oxygen, so 0, 0, 0, and 0. And the sulfur had a minus 2. Now remember, the sum of the formal charges should be the charge on the molecule. Sulfate has a charge of minus 2, or 2 minus, and so if you add these all up, they are minus 2. Okay, structure B. Okay, structure B, you had three double bonds and 1 single bond. And so that's B, and so they had a minus 1 on one of the oxygens, the single bond oxygen, and the sulfur had a minus 1. Okay. All right, so minus 1 is minus 2. The C structure had 2 single bonds and 2 double bonds for oxygen, so it had a minus 1 twice. And the sulfur had 6 valence electrons and 6 bonds. It had 2 double bonds and 1 single bond, and so the formal charge there is 0. All right, D, it had 3 single bonds of oxygens, and the sulfur had a plus 1, and E had all 4 single bond oxygens, 4 minus 1s, and plus 2 on the sulfur. Okay. Excuse me there. All right. Okay. Now, I'm only going to do this once. Anytime you see a double bond, it will have a pi and a sigma bond. And whenever you see a single bond, it will have a pi bond. If you have a triple bond, it'll be 2 pi bonds and 1 sigma bond. So this is the only structure here that I'll give that information. So what we want to do is decide which one of the structures is the best. So we look at formal charge, resonance, and octet, and then try to figure out which one's the best off of this information. Okay, as far as formal charge goes, okay, what you want to do is you want to have a structure that doesn't have a lot of formal charges. So what you do is, A structure only has one formal charge. Number two, and B and C have two, D and E have 4 and 5. So this would tell me that D and E are really not good in terms of formal charge. And they're probably the least acceptable structures because of that. Number one now looks like it only has one formal charge, but the issue is this. Even though it just has one formal charge, it's who that formal charge belongs to. It has a -2 on sulfur. Okay. Now, the outside atom is more electronegative, oxygen, and it would seem that you would like to have that form negative formal charge on the outside atoms, because they are the ones that tend to have more of the electrons. So this, even though it just has one formal charge, it's not a good place for it. So this is going to really reduce its possibility. Okay. So really kind of comes down, probably down to B or C. Okay. So now in terms of resonance, okay, number one of the things that knocks it out is it doesn't have resonance. Now you always want to have structure with resonance. Number 5 also doesn't have resonance. I say it does here, but it doesn't. So B, C, and D are the ones with resonance. So what we're going to come down, it's either going to be B, C, or D. Okay, A is knocked out for basically 2 reasons. It doesn't have resonance, and it's got the formal charge, negative formal charge on the wrong atom. We're knocking E off because it doesn't have has a lot of formal charge and no resonance. So B, C, and D. Which one is probably the best here? Okay, so let's look at formal charge and how it's situated. So look at B, C, and D. Okay, so all right, now C. Okay. B, it also puts a negative formal charge on sulfur, and I really don't like that. Okay, the thing about C, it puts the formal charge on oxygen and nothing on sulfur. All right, and that's probably your best scenario, is that we know there's going to be negative formal charge because this has a 2- charge, and you want to have that negative on the highly electronegative atom. So C is probably your best. Okay, it has two formal charges. B and C do, but what it does is it puts the formal charges on the oxygen, and both of these have resonance, but it's because of this formal charge. Now they all have 4 octets on the oxygens. Okay, so that doesn't seem to determine anything. So C is your best structure because it has resonance, has octet like everybody else, but the best thing about it is it puts has the least number of formal charges combined with where it puts formal charge. So it took a little bit thinking about how to do it. Okay, so next one is carbon dioxide, and I said you can come up with 2 structures. So the number of valence electrons is going to be 4 plus 6 plus 6, or 16. The skeletal structure looks like this right here. The outside of oxygen gets 2 bonds, 2 lone pairs. Count them up. 2, 4, 6, 8, 10, 12, 14, 16. That equals 16. You don't have to do anything funny with the oxygens, okay? All right, now you can get another structure here. You can have one of the double bonds move out, okay? And so I move this one out, and that can happen twice. So this guy, this structure can have another structure out. So this guy is a resonance structure. So carbon dioxide can have two different structures. It can have this structure here and this structure here, which is a resonance structure. No, I did this kind of messy here, but it says that this is a linear molecule. Okay, it has two attachments, no lone pairs. Okay, so you look up on the table. It says when you have two attachment, two lone pairs, and the hybrid is just going to be sp. Again, the polarity, we only have one type of bond here, a carbon-oxygen, and the polarity of the bonds, carbon will have as 2.5 going in the left direction, oxygen 3.5 going positive direction. So overall, there's a pull of electrons towards the oxygen of 1. We can figure out just by looking at the structure it's nonpolar because the carbon has the same things attached. It has oxygens, and so it's nonpolar. All right, next thing is figure out the formal charge and then figure out which one of the two structures is the best. So again, the bond at oxygen is the same as the previous example, has formal charge 0, the single bond at oxygen with 3 lone pair, -1. Okay, the carbon on the A structure has 2 double bonds, so it's 4 minus 4 bonds, -0 equals 0. And the carbon on B has only 3 bonds, a double bond and a single bond, so it's be 4 minus 3, or formal charge of plus. So if we put that all together over here, structure A has the oxygen 0, 0, 0, and a B structure has a -1 and a +1 on the carbons. So let's compare the two structures. Okay, now in terms of formal charge, right, B has 2 formal charges, A 0, so in this case that would make A a better structure because of that. In terms of resonance, B has resonance, so that's good. Usually resonance is that outweighs formal charge, but we're going to see that's probably not going to happen in this case. And the octet, A has all 3 atoms have an octet. Okay, and B, only 2 of them have octets. Okay, one of the carbon doesn't have an octet, just the oxygens. So the A structure is better because it has least formal charge. It only has 2, and it has 3 octets. So in this case, the resonance doesn't win out. Doesn't have enough influence to give the best structure. What I would like you to do is at least give me reasons on why you think it's the best structure. If you would have picked B as your best structure, and at least you would have to tell me why. Okay, just don't say it's B or A, but give me the reason why. If you give me B, say it's B, and you give me reasoning, and I'll give you almost full credit for it. But if you just say B, I'll go, I don't know why you came up with that. Or if you just say A, even though it's the right answer, again, I don't know why you came up with it. So give me your reasoning. I mean, that's part of this. It's just not to blindly plug things in and come up with an answer. What you want to do is figure it out. Okay, so I think I made a little mistake here, and I had to come back and do this. So let's go to nitrate. Okay. Saying I asked for 3 structures, but really there's only going to be 2 structures. So number of valence electrons is going to be 5, plus 6, plus 6, plus 6, and there's 1 extra electron, so there's 24. We put nitrogen in the middle, and give oxygen its number of lone pairs and bonds each, and it seems to work out 2, 4, 6, 8, 10, 12, 14, 16, 18, 24. Okay, good. But the problem is that nitrogen can't have any more than 8 electrons in its outer shell because it's in the second row. Second rows cannot have any more than 8 electrons because they have only s orbitals and s subshells, p subshell, and you can only put 8 electrons there. So, but this is not a hard thing to do. You don't have to cross this out, start all over. All you have to do is manipulate the oxygens, and so when you do that, you get you can manipulate them, and so you get this structure right here. Now, okay, and so just move the dots out, okay, and then you have your structures, okay. So if you count up to the now nitrogen has 8 electrons in its outer shell, 2, 4, 6, 8, and we still have 24 electrons. Okay, so we're all set. And if you notice, this structure can have resonance structure. Okay. There could be another structure as well, and now the other double bond come out, and then you can get this structure as well. Okay, so now when you look at that structure, it has a trigonoplanar shape, has 3 connections to nitrogen, 3 attachments, and a hybrid orbital on the nitrogen is sp2. The bond polarity is as such. This is when you look at it, it has the same things attached that we think could be a nonpolar molecule, but that's wrong. It's a charged molecule. Remember, a charged molecule will have this has a charge on it. It's NO3 minus, so it doesn't have a plus and minus in it. Okay, now the formal charges. So the formal charge of each oxygen with its double bond is going to be 0. With the single bond and 3 lone pairs, it's going to be -1. The nitrogen on number 1, it has 5 valence electrons and 4 bonds, so it has a formal charge of +1, and number 2 has formal charge of +2. Right, so if we look at the formal charges of all those guys together, you see that the H structure has 2 single bonded oxygens and 1 double bond, and the nitrogen has a +1 formal charge. Okay. So okay, and the B structure there's 3 single bond oxygens, and the nitrogen has +2. So when we put it all together, so the 2 different structures, structure A has 3 formal charges, and structure B has 4. So I would like to have the one less 3, and also A is better than B because B has a positive formal charge on oxygen, and that's typically not a good thing. So in terms of formal charge, A seems to be the best. A has resonance structure, and also it has all the atoms have octet, and in the B structure it only has 3. So obviously A is gonna be the best structure, the resonance structure. All right, now chlorine trifluoride. Okay, the number of valence electrons is 7 plus 3 times 7. They both atoms have all 4 atoms have 7 valence electrons, 28. You put chlorine in the middle because that's the least electronegativity. And then you give fluorine its number of bonds, lone pairs. Each fluorine has 1 bond and 3 lone pairs. You count them up, so this is that structure right here. So 2, 4, 6, 8, 2, 4, 6, 8. So this structure has 28. Not 28. It has 24. So 8 plus 8 plus 8 is 24. So we're missing 4 electrons, so we put those in the middle. So the chlorine has two lone pairs in the middle. Now, the structure blanked out what I have here, but it says the center atom has 5 attachments. Okay, so that means it's going to have a hybrid of sp3d. So it has sppd. Okay, so this will have a sp3d hybrid, the chlorine would. Now, if you look at the shape that corresponds to that is a T shape. It has 5 connections, 5 attachments. 3 of them are bonds, and 2 of them are lone pairs. Right. So, right, and the polarity of the bonds are like this. Now I sort of did this one the other way, and the most negative atom going this way. It doesn't matter which one you have going which. You could pick any one of these bonds. Okay, so I guess I picked this, like this bond here. I could have picked this one, and that way the F would have been over here. But overall, there's electrons being drawn towards the fluorine. Now this, if you added all these guys up, you would end up in the direction that overall they're all being pulled. You'd find that it's a polar molecule, but I told you there's a quick way to figure out. Usually, and we're going to see it at the end, there's a molecule that may not fit this case. Is if there's more than one thing attached to the center atom, we're pretty sure it's going to be polar. So this has a bond, fluorine, and a lone pair. So it looks like it's polar. The formal charges is each fluorine is 7 minus 1 number of bonds minus lone pairs is 6. The chlorine, it has 7 valence electrons, 3 bonds, and 4. Okay, so if you sum up the formal charges, 0, 0. Now this structure only has one structure that you could draw it. That I asked you to draw. Maybe there could have been others, but I just asked you to do this one. And so this is the only structure. So we're all done. Okay, PCl5. Okay, I think I might have actually done this one in the, and I have it here as PF5. Okay, so let's change that to PF5. Either way, you came up with the same structure. So it's 5 plus 5 times 7 is equal to 40. The skeletal structure, we put P in the middle. It's the least electronegative atom, and it's also the only atom. And put chlorine, fluorine, and its number of bonds and lone pairs. So each fluorine gets 1 bond and 3 lone pairs. And when you count them up, you have 40. So this is it. So this is your bonding structure. It has 5 attachments, just like the previous model. Okay, so it's also going to be SPPPD or SP3D. The shape it has 5 connections, and you'll see that's trigonal bipyramidal. And hopefully, if you look at the shape, you'll maybe you can figure out why that is. The bond polarity is going to be figured out here. This is a nonpolar molecule. The phosphorus has the same things attached to it. The formal charges are as such. Okay, pretty simple and straightforward. Okay, so let's go over nitric acid here. And so this structure here is a little bit more complicated, and you'll see in a second. It takes a little bit more thinking. You just can't rush through it and figure out an answer, because if you do that, you'll see that's wrong. So you've got to make checks to go along the way, and then try to figure it out. Okay, so we'll start out with simple. So nitric. So hydrogen has 1. Nitrogen has 5, and each oxygen has 6. So it's 1 plus 5 plus 3 times 6 is 24. And you make the skeletal structure, and then you give oxygen 2 lone pairs and two bonds, and you give the hydrogen 1 bond. Right, and then what you do is you count them out. You got 2, 4, you got 8 around each oxygen and 2 here, and you got 26. Now wait a second, okay? 24 and 26 don't match. Okay, what you can't do now, if your number was smaller, you could simply put dots on the structure. In this case, you just can't grab an electron and take it away. You can't just grab 2 electrons and take it away. So maybe you could, but so we know this is wrong, and it's wrong because it has 26 dots and you need 24. The other thing is there's just too many bonds on hot nitrogen. Nitrogen is in the second row, and the second row can only have 8 electrons in the outer shell. Okay, that's because it only has S and P subshells, and you can put 2 in the S and 6 in the P, so as many you can put in the second shell is 8. So you can't put, what is it, 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12, 13, 14. It looks like you're putting 14 electrons in the outer shell for nitrogen. Ain't gonna work. All right, so instead of just starting all over and go, it's crazy. Okay, let's think about it a little bit. Okay, let's look at what this substance is. So this substance is nitric acid. All right, so where does nitric acid come from? It comes from nitrate. What is an acid? An acid, and you learn this in 122 if you decide to take it, or corresponding class that talks more about acids and bases, is that an acid is a substance that when you put it in water, it will have a H plus removed from it. Okay. So nitric acid and nitrate are essentially the same molecule, except nitric acid has an H plus on it and the nitrate doesn't. So let's use that to our advantage. And that's one of the things we need to think about when we do these. So here's kind of, there may be a problem on a test like this. Okay. So if you see an acid, that comes from a polyatomic ion, a tertiary acid, what you need to do is you need to find out the structure of the polyatomic ion first. Okay, and then what you do is you put an H. Okay, so if it has a 1 minus charge, you'll put 1 H on. If it has 2 minus charge, like on the very first one of this sulfuric acid, you would put 2 H's on. Now, where do you put those? Where do you put them? You put them on the oxygen that has the 1 bond and 3 lone pairs. So don't put them on this guy up here. You'll put it on either one here. And it doesn't matter in this case which one you put it on. You could put the H over here or H over here. So what we do is we just put. So what you're doing is you're just essentially, there's a proton here, and then you're adding a proton to this one of these electrons, and it's basically you have an H hanging off here. Okay, so there you go. There's your structure, HNO3. So this molecule, right here has a negative charge on it, nitrate, and so what we do is we put an H plus on either one of these oxygens. And now we end up with this. Okay. And there's your structure. Now, so let's go over some of the other things, bond polarities and so forth. The bond polarity for this bond here, nitrogen oxygen, is the same as it was in nitrate. Okay. The shape around and the hybrid around this nitrogen is the same as it was in nitrate. So this is a trigonal planar, and it's sp2. Now, this oxygen here is a center atom. All right, so it has, and because it's a center atom, it can have a shape around it, and it can have a hybrid. Okay, the outside atoms don't don't have shapes around them. Okay, so this guy's trapped between bonds, so it has a shape. And so the shape is going to be bent. Okay, 2 bonds and 2 lone pairs, and the hybrid is going to be sp3. It has 4 attachments. SPPP. As far as polarity, it actually has, so this nitrogen has same things attached, so it looks nonpolar, but if you look at this oxygen is actually polar. It has an H, an HO, and it actually has 3 different things attached to it. It has H, lone pair of nitrogen, so that makes this whole molecule polar. Okay. And here's the formal charges. Okay, all the same formal charges as we saw with nitrate. Okay, but this time this oxygen here no longer has a minus 1. Okay, because it has 2 single bonds, and so now it's a 6 minus 2 minus 4 equals 0. Okay, next one is carbon tetrachloride. Okay, carbon tetrachloride, there's 4. Number of valence electrons is 4 plus 4 times 7 equals 32. The skeletal structure, put the carbon in the middle, chlorine's on the outside. Give chlorine its number of bonds and lone pairs, 1 and 3. Count them all up, you got 32. Okay. The center atom has 4 attachments, so it's sp3. The shape is tetrahedral. The bond polarity is 2.4, and I guess I'm just picking this bond here, but they're all going to be the same. So it's going to be 2.4, and it's going to be the electrons are going to be pulled toward the chlorine and by 0.6. The formal charges is carbon is 4 minus 4 minus 0. 4 bonds minus the valence electrons, 4 valence electrons minus 4 bonds minus no lone pairs, 0. And chlorine has valence electrons 7 minus 1 bond minus 6 dots equals 0, and that's each chlorine. So the overall, when you add up all the formal charge, 0, which is the charge on this molecule. And this molecule is a nonpolar molecule. It has the same things attached to the center atom. Okay, I3 minus, I decided I just want to do 1, and I'll tell you how many I want you to do on the test. This would just been, there's just too much moving around of electrons and so forth to come up with. But there's some key things here I want you to get out of this. So you have 3 times 7. Each iodine has 7 and plus 1. That's because it's charged. So this skeletal structure, and actually going to treat the outside iodines different than the center one. So we're going to do exactly what we did before. Is the outside atom gets its number of bonds and lone pairs. So iodine gets 1 bond, 3 lone pairs, each one. Then count them up: 2, 4, 6, 8, 10, 12, 14, 16. Okay, we said we needed 22. We're short 6. Where you put the 6? You put them in the middle. Here, here, and here. Okay. And now you're all set. Okay. Now, if we look at the molecule, we'll see that it has, it has, the center atom has 1, 2, 3, 4, 5 things attached, 2 bonds and 3 lone pairs. So that means the hybrid is going to be SPPPD, SP3D. When you look at this chart, it's kind of strange, is that this is a linear molecule. Okay, and hopefully you can see why. There's these molecules on above and below kind of force this structure to be just straight. There's no bond polarities here. Okay, they all cancel each other out because it's all i's, I minus I. So whatever i's polarity minus this is, so the bond polarity, the difference in bond polarities is going to be 0. Again, this is a polar molecule. I mean, neither. It's neither polar or nonpolar because it has a charge. And if you look closely, It's a linear molecule. And even though, so if it didn't have a charge, you may go, it's a polar molecule, because it has different things attached. It has bonds and lone pairs. Well, this one's, you have to be more careful about this when you have to actually look at the structure. This is a linear molecule, and it turns out is that linear molecules, if they have the same things attached to both ends, are going to be nonpolar. But this is a charged molecule. But if it did not have a charge, it would be a nonpolar molecule, even though it has different things attached. So the general rule I came up with is when the center atom has different things attached as polar, it doesn't always work. You have to look at it a little more closely. The formal charges on the oxygens, on the iodines, on the outside ones, it's going to be 7. That's number of valence electrons minus number of bonds, 1, minus number of lone pairs, 6. Dot 6 equals 0. And the center one has 7. Did some bad math here. So it has 7 minus 2 minus 5. So did some bad math here. Yeah, that's wrong. This should be 7 minus 2 minus 6, which is minus 1. Okay. All right. And maybe I can fix that when I'm done here. Okay, so the last one is Xenon Tetrafluoride. Now, this one's kind of weird because it has a noble gas and it's a covalent molecule. All right. So, and we are always taught that noble gases are inert and don't react. Well, they can, especially the big ones. Xenon is in the 6th row. Okay, that means it's a really big molecule, and that means those valence electrons that are sitting way out actually can be attacked by a highly electronegative atom like fluorine. Okay, so this can actually happen. So number of valence electrons, xenon has 8. Then you have 4 times 7, and then so there's 36. So here's your structure. Got skeletal structure. Then give each fluorine 1 bond, 3 electrons. Okay, and then when you get done, you count them all up. You get 8, 16, 24, 32. You're short 4, so put those 2, 4 in the middle. And so now what you have is the structure. Okay, and you look at it. How many attachments xenon has? It has 4 bonds and 2 lone pairs. So it has 6 attachments. So the hybrid is going to be SPPP and then 2 Ds. Okay, so sp3d2. So when you look at the charts, it's the structure with 6 connections. When you look at the chart, this is when you look for the one that has 4 connections and 2 lone pairs. This would be a square planar. We can't figure out the polarity of the bonds because our electronegativity table doesn't give a polarity for xenon. Okay, so you can't do that. Is this a polar or non-polar molecule? Okay, now again, this is going to be exception to the rule. So if you look at it, you would go, oh, it has the center atom has different things attached to it. It has for fluorine and a lone pair. Okay, but this is going to end up being a nonpolar molecule. If you look at the structure, you'll see that all 4 of these fluorines are all sitting in the same plane. That's why they call it planar and square. Okay, and these 2 lone pairs are sitting on top, and one sits below it, the plane, and another one sits at the top of the plane. So all these guys cancel each other out, and so this ends up being actually a nonpolar molecule. So again, the general rule is, especially for molecules that have less than 4 attachments. Okay, once it gets 5 attachments, 6 attachments, you have to think a little bit more about it. All right, the formal charges, xenon is 8 minus 4 bonds and it's 4 lone pairs, 0, and fluorine 7 minus 1 minus 6, that should be, equals 0. Okay. All right, so hopefully it'll come out, that'll cover it, and I'll double check it before I send it out. If this is it, then I will send out the the final test part of this test worksheet, and don't send me this worksheet I sent you, but send me your test. And again, wish we could have stayed together for the whole semester and done labs, because that's really I think one of the key things about this class. And if you're around for in the winter, a year from now, next spring, 122 is offered. Take it. You can take it from me, and we can. And that's a really good lab class. That class has a lot of labs. And if not, and this is the last time I see you guys, good luck to whatever you do. I know the basketball people. Sorry about your season. But you guys did real well, and good luck with all the things you do. All right. Scully's out and over. Bye.